All right, now find intervals where the function is concave up or concave down. So remember, to test concavity intervals, you want to find the second derivative, set that equal to 0 to find your possible points of inflection, then test each interval to see if the function is concave up or concave down. So we do need to remind ourselves of how to differentiate a natural log function. So the derivative of a natural log function, let's just say ln of x by itself is 1 over x. However, notice there's the argument here is x squared plus 1. So the derivative with respect to x of natural log of u is going to be 1 over u times du over dx. I like to think about this way, u prime over u, or the derivative of the argument over the argument. H prime is going to be the derivative of the inside, which is the derivative of x squared plus 1 is going to be 2x, over the inside, which is x squared plus 1. There's your first derivative, just like that. Now, please be careful. You cannot reduce anything here. From here, take the second derivative. Now, notice this is a rational function. Therefore, you have to use your quotient rule. So, h double prime is going to be low d high. So, low is x squared plus 1 times the derivative of the high, which is just 2, minus high, which is 2x, times the derivative of the low. The derivative of x squared plus 1 is 2x, all over low squared. Now, this is going to be really nice because x squared plus 1 is always going to be positive. Therefore, we just need to simplify the numerator just a little bit, set it equal to 0 to find our possible points of inflection. All right, so we'll distribute this 2 here. We get 2x squared plus 2. And then 2x times 2x over here is 4x squared, but that minus is sitting there, so minus 4x squared all over x squared plus 1 squared. Clean it up just a little bit more. Combine your 2x squared and negative 4x squared, you get negative 2x squared plus 2 over x squared plus 1 squared. All right, you could factor out a 2 here. You can do a little bit more algebra, but remember, what you want to do is find your possible points of inflection. And so you do that by finding values of x that make your second derivative equal 0. So let's just take the numerator, set it equal to 0, such as this. We'll solve that. So to solve this, let's go ahead and add over that negative 2x squared. When we do that, we'll have 2x squared on the left equals 2. Divide by 2, you get x squared equals 1. And then take the square root of 1, you'll have x is equal to negative 1, x is equal to positive 1. So now we want to test each of these intervals that are broken up by negative 1 and 1. So let's go to our number line and break up the real number line into these 3 intervals. So here's x equals negative 1, x equals 1. Let's just take those factors of the second derivative and write them over on the left side. So we got negative 2x squared plus 1. Plus 2, sorry. And then again, the denominator, x squared plus 1, can never be negative because x squared, anything squared is positive, so it doesn't matter what you plug in for x. That will always be positive, so there's really nothing that I need to test there. Basically, I just need to test the top, so it's going to be a pretty quick test. We also need to think about natural logs and their domain. Remember, the domain of a log is the inside, or the argument must be greater than 0. Using that same logic, x squared plus 1 can never be negative, and so the domain here would be all real numbers. There's no way to make that equal 0 or any negative number. So we'll continue this. Result is just going to be that one test, but let's get in the habit of doing this. All right, find numbers in each of these intervals. So we got negative 5, we got 0, we got 5. if I take -5 and plug it in, now be careful, -5 will be squared, so it'll be positive 25 times a -2 is -50 plus 2 is negative. All right, so of course the result will be negative. If I plug 0 in for x squared, I'll have positive 2. So boom, boom. Again, if I plug in positive 5 into x, that will result in a negative. So in this sign chart, wherever, because we're testing for intervals where a function's concave up or concave down, we'll say h of x is concave up on the interval -1 to 1, and h of x is concave down on two intervals. We'll say -infinity to -1, and again from 1 to infinity.